Is about augmentations and shifts. So I think I'd better start by recalling some general features which maybe should be helpful to understand what this paper is all about, or what is the motivation of constructing the Org plus category and interpret as shifts. So recall that any Weinstein manifold can be constructed from a disk, because in this paper we are talking about like knots in R3, so we only care about D4, or the Weinstein manifolds are four-dimensional, and we assume that maybe there is no subcritical handles, so all the handles are critical, and they contribute to the symplectic topology of your Weinstein manifold handle attachment. But there are another class of interesting symplectic manifolds which could also be obtained by attaching something to this D4. So these are called Liouville sectors in the paper of GPS, Garnard, Chapardo, and Shandon. So let me, so Liouville sectors somehow should be regarded as like local pieces of Weinstein manifolds, and there is a local to global principle to generating the replica category. So let me illustrate the situation by using the simplest example of a Hopf link. So suppose you have this Hopf link inside R3, and what you can do is that you can attach handles along this Hopf link, and you can choose to not to attach handles but attach a cotangent comb along any component of this Hopf link, and this would give you several inequivalent symplectic manifolds which are Liouville sectors. So the first one, if we only attach cotangent combs and to both of these components of a Hopf link, then what we would get is basically R4. And the Lagrangian Skeleton is just the union of two Lagrangian disks. By Lagrangian Skeleton, I mean, so in the case of Liouville manifolds or Liouville sectors, you can use the negative Liouville flow to retract your symplectic manifold. So that would give you some Lagrangian submanifold. But for Liouville sectors, this is more complicated. So what I mean is that this basically its infinitesimal Foucault category has these two Lagrangian disks as its objects, and we can choose to attach a two handle to one component of the Hopf link, and we attach cotangent combs to another. And this would basically give you cotangent bundle of S2 and plumb with cotangent bundle of R2. And the Lagrangian skeleton looks like this. So we have a Lagrangian sphere and a Lagrangian disk intersecting transverse. So the reason is that if you attach handle, so assume this is your disk, four-dimensional disk, and you attach handle. So the original Lagrangian disk inside your D4 would be capped off to a Lagrangian sphere. So that's why this is a way of constructing compact Lagrangian submanifolds. And for the last case, you attach handles for both of the Hopf links, and it would give you a Lagrangian skeleton looks like this. And the corresponding symplectic manifold is just a plumbing of two copies of cotangent bundle of S2, and this is usually called the A2 monofiber. So you can see in all these three cases, you can define the so-called infinitesimal Foucault category, or just the Foucault category. And in all these three cases, you can define the corresponding wrapped Foucault category.
Sorry, with the connected sum, you mean sort of
plumbing. You identify fiber direction and base direction of those two cotangent bundles. Yes. So basically, in this case, all you can get are just because it's so in the language of partially wrapped Foucault category, you put stops on both of these components of the links. So what you get is a finite dimensional wrapped Foucault category, and of course the corresponding Foucault category is also finite dimensional. And this is basically what we are doing for Org plus. And for the second case, it's just a version of partially wrapped Foucault category, which is called cotangent bundle of S2, stopped at one component of this Hopf link in the paper of Sylvan. And for the third case, it's somehow Org minus, but you need to adjoining units E minus and sorry, should not write like this. It's just arc minus, and you can adjoining units. Then you get like in not 4. This is just embedding into your compact Foucault category of this A2 mu not 5. So I mean, in the middle case, there should also exist some augmentation category which should be interpreted as sheaves, but currently there is no work on this. So I'd like to recall a little bit on the paper of Ekholm and Eliash. Ekholm and Kibi. But I'm not going to talk too much about that. So according to their paper, the infinitesimal Foucault category of a Liouville manifold associated to a Legendre link lambda. So you can determine this Legendre link. Every component you attach a sign, plus sign or minus sign. On the plus side you attach a tangent cone, and on the minus side you attach two handle. So this gives you somehow a symplectic Liouville sector called x lambda, and you can define its infinitesimal Foucault category. And one of the results in the paper of Ekholm Lakidi is that this category can be constructed by taking the bar construction of your wrapped Foucault category of this Liouville sector, or partially wrapped Foucault category, whatever, and then taking linear dual. So recall that bar construction gives you somehow in this case DG coalgebra, and when you take the linear dual, it gives you a infinite algebra. So from this point of view, well, I should say that this is just generalization of the facts that you can somehow construct the chain complexes on your manifold by looking at the chain complexes on its space on its space. Sorry, on the space loop space. So I mean, it's just like you only consider one, only consider unknown or one copy of cotangent bond. So by applying its theorems, they are equivalent. So this is basically how you can construct this infinitesimal Foucault category, and it should be the guiding principle of construct arc plus. So recall that basically by the results of BEE, Bourgeois, Ekholm, and Eliashberg, this arc plus should somehow be constructed by using Chekhanov-Eliashberg algebra of the Legendre link, and then take linear dual. So this is basically what these 5 authors are doing in their paper, and but they write it in a very concrete, very concrete language, so that you can actually do explicit computations.
Yeah. Why is this not arc minus?
Where is
Because you gotta explain what's being punctured and what's not. It depends on lambda. Depends on what you do to lambda.
Yes. So
that's only true if you puncture lambda.
So I'm assuming that all the lambda all the components in lambda have a minus sign. So lambda is like served as a stop.
No,
So
but
which means that you attach
Totally enough. If it's a symbol.
attach cones
Ah, let's stop. Okay.
all the components of lambda.
Minus is if you do it.
So this should give you the arc plus category.
Okay.
Sorry, this is a mistake. So recall that. So I want to recall another fact that in their paper, the partially wrapped Foucault categories is interpreted as Chekhanov-Eliashberg algebra. With loop space coefficients. So in our case, this is pretty easy to do, because in our case we're only considering Legendre knots and Legendre knots and links. So I mean, since every
Just so you know, if you're pressed for time, then this will be covered in detail tomorrow.
I know.
actually doing the loop
Yeah,
space
but I want to illustrate why we need to choose base points on Legendre knots.
Oh, okay.
Yeah.
But
So
you don't need any of these. It's local systems like local monodromy in the sheet.
yes, but somehow, I mean, it's a tricky thing that you have different versions of Chekhanov-Eliashberg algebras, and they are defined using different coefficients. But I mean, to make people understand why should we use actually Chekhanov-Eliashberg algebra with coefficients in the Laurent polynomial ring. I think I better mention this. I mean, this is I mean, how to help people understand the relationship between this paper and the paper of Ekholm-Lakili. So sorry. So this is just the loop space coefficients of S1. That's why we need for every component of lambda a base point star I. So now the Chekhov-Ashburn algebra is generated over field K. So we fix the field to work with, although the construction works in for general commutative rings. So you have reports A1 to AR, which can be seen as crossings in the Lagrangian projection. And you would join in new generators like TI inverse, like from I to M. But you can see this algebra is not free because we require an additional relationship between Ti and Ty inverse. But a free model can definitely be found. It has 5 generators, and you can find it in the paper of Ekholm and Lakili. So we have this Chekhov-Ashburn algebra, and the differential is defined in the usual way, but with the additional condition that the differential of Ti and Ty inverse should vanish. And of course, we can also define a Maslov potential on this Legendring, and we assume that this Legendring has no rotation number 0, so that you can have a C-graded Chekhov-Ashburn algebra. And for example, this is the case of an unknot or trefoil knot and many other cases. So, but for the generator Ti and Ti inverse, we assume that their gradients are 0. So this is basically the version of Chekhov-Ashburn algebra we are using. So let me recall a little bit about the definition of differential. So you have you can associate to any crossing 2 kinds of size. One kind of size Reap sign, the other kind is orientation sign. So when you count holomorphic disks, you just count those with a single positive Reap sign, and all the other corners should have like negative Reap sign. And when you count holomorphic disks, you use these orientation signs to determine whether your coefficients before your word in the differential is positive or negative. So in this way, you can define your Chekhov-Ashburn algebra. So this is the introduction of the Chekhov-Ashburn algebra that they are using, and their augmentation category are just constructed in this Chekhov-Ashburn algebra. So another important issue is that we need to have link gradings on Chekhov-Ashburn algebra, which means that you have a Legendring link and you decompose it as different components. Note that each component does not need to be a knot, and it can be a link. Just give them a number, and so you can, with this link grading, I mean you can, so we denote by R the set of Reap chords which are serving as generators of the Chekhov-Ashburn algebra, and we denote by Rij, which means the chords end at I and starting at J. And recall that we also have like additional generators Ti and Ti inverse, and so we get a decomposition of T. But in this case, we don't have like mixed generators. For Reap chords, we have mixed Reap chords which begins and ends at different components of your Legendring link. But for T, we just use Tii, and Tii denotes the corresponds to generators to Ti or Ti inverse on the component lambda I. So sorry, I should say that here we fix a base point. So usually this base point we fix at the right cusp of your Legendring. knot, and we only need like one base point for each knot that's enough. And this, so since you have the link grading, it can be verified that if A is a report, then DA only contains composable words. So if you take the differential, it means that you can write them as composable words. Say A is a report in Rij, then it's a composable word from lambda I to lambda j, which means that you can have many intermediate reports, but they are somehow if one is like coming from Rik and Rik plus 1, and the next one comes from Rik plus 1 and Rik plus 2, things like that. So this definition of link grading can be generalized to any semi-free linear algebra, which means that you ignore the differential, it's a free algebra, but then you have the differential and with generating set. Equal to, so always denote the generating set by S. So by generating set it means R and disjoint union with the T's coming from the base points we have chosen. So suppose we have like decomposition of this set into R and T, and a link grading is just a pairing of maps from the generating set of S to the set of M elements. So this M corresponds to the number of components here. And we will propose that for A belongs to R, which means geometrically that A is a report with RA not equal to CA, which means that it's a mixed report. Then each term in DA is integer multiple. So in this case, not necessarily, yes, it's an integer multiple of composable words. And if A is not mixed, which is a pure report, then instead of like composable words, we also allow constants, which means you have an integer multiple of the identity. And we require that these link gradings for Ti and Ti inverse, for Ti are Ti inverse, they are all the same. So this is actually an abstract generalization of the geometric situation, so that they can like write their construction in a quite uniform way.
So are you requiring this property of containing only composable words, or?
No, not requiring. It's in geometric case it can be proved that the differential of any report can be written as a direct, as a sum of composable words.
So I don't know if you're going to get to this later, but can you give me a quick, like a geometric intuition of what this property is useful for?
Where this property is useful because you need to deal with A infinity structures in the augmentation category. Then you can show that you were so I mean this is correspond to the composition in A infinity category. So if you have a infinity category and you have like objects like x1, x2, then you somehow want to like compose it with form x2, x3. then something like that. So you can see this is composable. I mean, this link gradient is just to use to define this. I mean, this is somehow I mean, you should have requirements, and you can expect to have an A infinity structure. Otherwise, it is not even expected. So that, I mean, later you would need to take like m copies of your Legendre knots. So this is the analog of taking the bar construction algebraically. But when you are taking m copy, you need to have a link gradient to separate those three parts. So recall that we already have the like algebraic motivations that the augmentation category should be constructed by applying bar construction and then taking linear dual. So that's why this makes the concept of co-derivation on the reduced tensor algebra extremely important. So the reduced tensor algebra, so we shall take the reduced tensor algebra of A infinity algebra with degree shifted down by 1. So it's just reduced. By reduce, I just mean you cancel the copy of K inside the definition of a tensor coalgebra. So this is called reduced tensor coalgebra. And somehow a derivation of this reduced tensor coalgebra is just the degree 1 map co-derivation, which satisfies the co-Leibniz rule. Then you can define operation MK on the case tensor copy of the A infinity algebra by setting S, which is so I should define S to be a degree shift map, which is trying to shift the degree down by 1. So we put S composed with MK equals BK composed with SK. So by BK, we mean the case graded component of B. Then the requirement that MK satisfy A infinity relations is equivalent to the fact that B is a codifferential, which means that the square of B equals 0. So recall that we are using a kind of different version of Chekhov-Ellashberg algebra, which is the Chekhov-Ellashberg algebra with loop space coefficients in S1. So if we want to recover the Chekhov-Ellashberg algebra, you only need to take, which is we define to be A epsilon. We take the quotient of A by the ideal generated by Ti minus epsilon Ti with epsilon augmentation. So this cancels the generators which come from base points and gives you the usual Chekhov-Ellashberg algebra, which is defined over K without the Ti generators. So it's clear that we have a decomposition that A epsilon is basically generated by 3 chords. So C is a K-vector space spanned by R. But for this talk, we only use this original version of Chekhov-Ellashberg algebra to define the linearized contact homology. And this is the only usage of this algebra. So to see how to define the linearized contact homology, we write A plus epsilon to be the positively graded part inside A epsilon. which means that you need to have a reap chord or a composable of words of reap chords. Sorry, a word of reap chords which sits inside the case copy tensor of the vector space C. And then you can define automorphism on this Chicano-Eliashko algebra by sending every generator A to A plus epsilon. And you can conjugate your differential using this automorphism. So this one acts on the usual Chicano-Eliashko algebra. Then it can be verified that.
Oh wait, so before you erase this, so just for me to understand, the point is you had an algebra A, and with curve counts you define the infinity operations.
Yes.
Then you take the reduced bar construction.
Yes.
Which wasn't really that one, because you want to use probably that augmentation to reduce each of the pieces that still have a unit, because otherwise that's not a unital algebra. But anyway, the point is that you substitute.
Whereas the existence of unit comes from the fact that your algebra is augmented.
Yes.
So when you take co-algebra, you get a co-unit. Then you take linear dual, you get a unit.
So are these two blackboards just saying I gather the infinity operations as a DG algebra?
Yeah. Yes. So we can somehow define the linearized content homology. So one can verify that the epsilon preserves the positive graded part inside this usual version of Chicano-Eliashko algebra. And then it descends to a differential of quotient by A plus epsilon squared. So this is just this complex is d epsilon. It's just the linearized epsilon. So the reason we are interested in this, I guess, come from Seidel's isomorphism, because Seidel somehow proves that the linearized LCH recovers the Lagrangian flow homology of your XL Lagrangian submanifold. So since it's exact, it reduces to cohomology. So now we can take the dual vector space C star, which is just the dual vector space of C, and somehow you can extend the pairing between C and C star to TC and TC star. Which is defined by taking these words so this one is Q. And now you get a co-differential on the reduced tensor coalgebra of C star. But somehow we want to keep the original notation, so we set like C check equals C star shifted up by 1. So this is just the reduced tensor coalgebra of C check 1. So this is defined by taking the differential d epsilon, and you take its dual using the pairing on this tensor coalgebra. So once you have a codifferential on this reduced tensor coalgebra, you will have a infinity relations mk. Note that this is determined by the augmentation epsilon, and this is defined on C check. So recall that this C check, so it's dual space C with some degree shift is just spanned by reap chords, and so originally it may look a little bit strange that you only need like reap chords, because later I'll talk about this later. So for now you just remember that if you have a reduced tensor coalgebra and you get a codifferential, you can define the A infinity operations. So now we can define the so-called augmentation category for somehow consistent sequence of DG algebras. So somehow this consistent sequence of DG algebras basically says that you have a link grading on the generating set, and somehow they are compatible. So I think I need to write down the formal definition. So a sequence AI of DG algebras with generating set S is consistent if, so the first requirement is that the first requirement is we have a semi-cosimplicial set S with, so this semi-cosimplicial set is a functor which I will define independently later. I mean, but if you think in the geometric situation, it basically means that you are taking m parallel copies of a Legendre link, and every copy is the same. So you can actually identify the reap chords like C12, or like C23, and C34, and this is just basically the notion of. So that's why why you need this identification is that you needed to reduce the definition of the A infinity structure to the kind of A infinity structure on the like linearized Legendre content homology its dual. So that's why you need this consistent sequence of DG algebras. And if you want to think it concretely, you can just regard it as a sequence of Chekhov-Ellashberg algebras defined by like I copies of the same component of lambda. And these I copies are basically, you move a little bit using the reap flow in the positive reap direction. So you get something like that. And they're leveled from top to bottom. So this is a concrete model of a sequence of consistent DG algebras. And you can see that if you have like 3 copies of your Legendre unknown lambda, then you have more cores and more generators in your Chekhov-Ellashberg algebra. But one thing that is unchanged is that if you like include the generators of these 2 copies into these 3 copies, then their differential are essentially unchanged. So actually you get some embedding of the DG algebras. So that's basically why we need this notion of consistent DG algebras. So another condition is that we need link gradings on the generating sets of this sequence of DG algebras. So sorry, I need to introduce some notation. So if you don't like this SM just means the generator of the Chekhov-Ellashberg algebra with m parallel copies of lambda. And this M is just a set of M elements, and this N is just a set of N elements. So we have a category delta plus whose objects are a set of M elements. So we denote the set of elements, M elements, by this bracket M. And the morphisms are order preserving inclusions. So it's very important to preserve the order if you are familiar with the definition of Orc-minus category, because the level of their Legendre links are from bottom to top. And a semi-cosimplicial set, which is denoted by code delta plus set, is a function from delta plus to any category C. And in particular, C can be the category of sets. And somehow you write, so if given a semi-cosimplicial object, you can write like X, we can write Xm to be the image of the set of M elements on the X. And you have an induced map. If you have like M less than N, and you include the set of M elements into the set of N elements, you get a somehow natural transformation between. Sorry, it's not natural. You get a map between Xm and Xn. So this gives you the condition to somehow transfer the A infinity structure on C check to the A infinity structure on the augmentation category. So let AI be a consistent sequence of DG algebras. And then we have a map HI which stands like AI to AMI. So recall that AI is the Chicano-Felsberg algebra built from one copy of your Legendre link, and AM is you use m parallel copies of this Legendre link. So you get this map, and this map is a quasi-isomorphism. So this HI, recall that this HI means that you somehow include the generators of this one copy into the generators of this m copy of your Legendre links. That's why it gives you a quasi-isomorphism. And you have Hij, which identifies S2 with its image in SM. Recall that SM is just the generating set of this DG algebra AM. And this gives you a isomorphism between C12 check and Cij check. So that's why I said you only need like C12 check, which is like one copy of the reef chords rather than all the copies which are denoted by Cij check. And this seems to be a little bit strange because you are building the whole category using like all the reef chords which ends as the first component and starts as the second component. But this does not seem to be strange if you remember the fact that if you have a like Weinstein manifold, then you have the like attaching links, which means you attach critical handles along that link. Then somehow you know the attaching links and you know the somehow intersection form or thinking diagram of this symplectic four manifold, Weinstein four manifold. So I think that's the reason, because somehow knowing a Legendre attaching link is knowing the intersection of the Lagrangian skeletons. That's why it somehow determines your A infinity structure. single-handed. So you have this isomorphism, and then you can define your A infinity composition. So if you have like C12 check and you tensor several copies of C12 check, and this is the formulation that we use to prove that C12 check is an A infinity algebra. Then you can use these identification maps Hij to send these vector spaces to Ik plus 1 check tensor to Ci1 Ci2 check, and then you can somehow act on. So somehow, if you want to define this augmentation category, you need, because it's M copies. Sorry. So you need an augmentation of this M copy Chekhov-Elashko algebra of like M parallel copies of your Legendre link. So that's why you need an augmentation from AM to K. And this can be built by assigning. So this can be built from augmentations of your original algebra A1. So if you like pick any augmentation epsilon I from your augmentation A1, then you just put them together and you get an augmentation of this M copy algebra AM. So this is basically because the geometric reasons that you are using M parallel copies of your Legendre link. So finally, you would get an augmentation on this algebra, and somehow this augmentation would give you an A infinity structure from the direct sum of like Cij check, and you tensor it by m times, so then it's going to send it to like Cij check. But you can prove that all the A infinity maps are zero except for these kind of things. That's why it's going to give you an A infinity category, because it's actually composition of the morphisms from like epsilon I1 to epsilon I2, and finally composed epsilon Ik to epsilon Ik plus 1. So finally you get an element in Ci1 Ik plus 1 check. And somehow you can use the identification Hij to send it back to C12 check. So that's the A infinity structure on the augmentation category. It can be defined for any consistent sequence of UG algebras, and in particular, it can be applied to the Chekhov-Elashko algebras built from M parallel Legendre links. So apply the above construction.
So, sorry. Let's suppose that I only send the previous talk. Could we start there and do something that goes from augmentation to sheets? Or it's just that there's not much time left. No, it's just that I feel there's only half an hour left. And maybe sheets. Maybe we do it if we come
I think I'll just repeat it.
But it'd be good to understand like through it.
Well, I will say something about that. But let me just finish this. So apply this construction to the Chekhov-Elashko algebras constructed from M copy of your Legendre link, and this will give you the definition of the augmentation category, which we denote by of plus of lambda. And somehow you need to choose a grading, which is your Maslov potential. So it gives you an A infinity algebra, which should recover the Lagrangian flow algebra, or the infinitesimal Fourier category built from the Lagrangian fields. So I'll give you one example, which is the case of unknot. So in the case of unknot, if you want to compute this, sorry, I need to say that you have two ways to define this Chekhov-Elashko algebra. So I'll say very briefly. So one way is to use the front projection, and it will give you like transverse intersections, and you use ins resolution to transfer it to the Lagrangian projection, and you just read the differentials from the Lagrangian projection. Another way to start with the Lagrangian projection, since in this case your Lagrangian link are like they are only different, so you take m copies of Lagrangian link that are only different in the z direction, so that you actually cannot see it. So the way to do it in this case using Lagrangian projection is that you do a splash construction or dip construction, that's the same. So you can get something to compute. So it's something that you can compute. So let me let me do it for the case of unknown, and in this case we use the second perturbation method, which gives you basically a Lagrangian projection like this. It's on the ground. So you can see you do a splash construction here, and it's going to give you some new reef chords, which we can denote by x12 and y12. So recall that the morphism spaces between like any augmentations are defined by this C12 check.
Can you label which one is lambda 1 and which one is lambda 2?
This one. So this one is lambda 1, the outside one is lambda 2. So we choose base points. So the good point of like the Lagrangian projection is that you can read everything from diagram just to use the reef size and orientation size, and you can write down all the differentials of the Chekhov-Elashko algebra. So we're computing the Chekhov-Elashko algebra of this 2 copy, which is 2 copy of unknowns. So you write it down with this E1 inverse. So since we have lambda 1, lambda 2, we have reef chord as generators, which are labeled here, and we have like base points which correspond to T1 and T2, and BA12 equals minus x1 y1. So from this, it follows immediately from definition that the degree 0 part so in this case you have only one augmentation. You have a unique augmentation for the unknown, which sends your reef chords to 0 and which sends your generator to -1. So this is generated by y plus, and this y plus will give the unit of your augmentation factor. So degree 1 part is generated by x plus, and degree 2 part is generated by a plus. And somehow you can compute the differentials. It's just the computation of usual linearized contact homology. So you can compute it by linearizing the differential and then taking the due. So from this you find that somehow d epsilon linearized A12. So we are using like two same augmentations to like define the bilinearized content homology, so it recovers the linearized content homology. And we have this X12. So these things live in C12. Check. Equals 0 and the C differential y12 equals 0. So from this you take the dual. So A12 check. A12 check is just a reef code which end at the first component, starts at the second component. So you're dualizing these differentials, and you get M1 in your augmentation category of your X plus equals A plus, which means that these two generators can be cancelled, and the remaining one is just this Y plus, which is a unit. And this gives the local homology of a two disk inside R4, which is just expected. So I mean, this is definitely not the replica category. If you compute replica category or the compact Fukara category inside R4, it's definitely going to give you 0. But there is one case that you don't get 0, which is to like use the Fukara-Seidel category, and you regard that Lagrangian disk as a left-shed symbol, then self-local homology is rank 1. And yes, that's basically the story.
Can you
But
repeat this last minute?
huh?
So you're saying that these, I should think of it as the ball, and then C2 fibering over C, and then
Yes.
computing.
X square plus Y square.
Yes, and then we're computing the cells.
Yes, because I mean the
What are we computing?
the thing, so Fukara-Seidel and infinitesimal Fukara category are not the same, because Fukara-Seidel is directed, but somehow the Bayesian methods are the same. So you use the Bayesian which has like very small slope at infinity. That's why when you define itself. So you start with the standard left shed vibration on C2, and it can be regarded as a symbol of your left shed vibration. You have a unique critical point, and then your Lagrangian is like this. And when you do Bayesian, you just use the perturbation which is very small at infinity, and you get this one. So this is perturbed Lagrangian, this is the original Lagrangian. You get a rank 1 morphism space. So this is how you define the local homology of left shed symbol. But somehow in the Fukara-Seidel case, you are going to like make it directed artificially, because you are going to match the like derived categorical coherent shifts of a final surface or something like that. But if you use the same perturbation scheme to define like local homologies, I think they're just the same basically as you do in the infinitesimal Fukara category. At least for self-morphism, it's the same.
So I should be thinking of, we start with the ball,
Yes.
and then once you have one and not, this ball before becomes T star 2,
Yes.
and then when I attach puncture the second one, then this is the fiber of the Manchester vibration, and so it should stop there and take the filling, and that's the
So, and you can also compute M2 for this unknot, which means you need to like compute the Chekhov-Eliashberg algebra of the 3 copy of an unknot. So I cannot draw this because the picture is too complicated, but I'll just tell you the result. So the M2 inside this category will generate X plus, A plus, and Y plus. Sorry, I should mention that for generators AI, Xi, X12, A12, and Y12, they are sitting inside the vector space spanned by reef called C12. But when we take the C12 check, then they should be denoted by X plus, A plus, and Y plus. This is the convention in their paper. So this is somehow also easy to compute. Just to use epsilon to augment your generators, which means to set every t in your computation to be -1. Then you are going to easily get this result from the differential inside this Chekhov-Eliashberg algebra. So you can see the y plus plays the role of a strict unit. So in this case, this augmentation category not only has a cohomological unit, but it actually has a strict unit, which is not exactly the same as in the case of classical Foucault categories. There is a minus sign here, because for Foucault categories it's only cohomologically unital. But somehow you can find an infinite category which is quasi-isomorphic to that one, which is strictly unital. So that's why, so it's like originally your infinity structure is defined on flow complexes, but can be descend to flow cohomology. So we have finished the computation of this example. Now I should say at least one word about how these things are interpreted as sheaves. So the statement is that your augmentation category, basically, of your Legendrian link with theorem has you require every component to have rotation number 0, so it's C graded. Should be isomorphic to C1 lambda u, which is sitting inside the category of constructible sheaves on, in this case, like R2 lambda. So you already know this notion from Dawn's talk this morning. And this C means that your sheaf is completely supported in R2, and this C1 means microlocal rank 1. So it can be defined by some way, but I should say that why we consider microlocal rank 1. The reason is that if you refer to the original paper of Nadler-Zaslow, they are going to tell you an isomorphism between the Foucault category of a quaternion bundle with the sheaf category. But in their version of the Foucault category, your Lagrangian branes are allowed to equip with arbitrary rank local systems. But somehow, if you recall the definition of the flow chain complex, if you equip it with higher rank local system, it's going to affect the dimension of your morphism spaces. If you want to keep these morphism space in your augmentation category or class, then you are going to equip these Lagrangian submanifolds with only rank 1 local systems. That's why we need like the notion of micro local rank 1. And the key point of the proof is so in my mind should be the Sivak's construction of the bordered Chekhanov-Elashberg algebra. So basically it allows you to define a Chekhanov-Elashberg DG algebra for Legendrian tangle instead of a knot. So to define this algebra, somehow you need to like join in some new generators for the. So say we have a Legendrian tangle like this. So if we have a Legendrian tangle like this in an open neighborhood, then you need to like allow pairings between different strands. So if we label the strands from up to bottom, like from 1, 2, 3, 4, 5, and we will allow generators which are written like Aij, which correspond to a pairing of strands with I less than j. So this is also kind of splash construction. You just take half of the splash construction and you define the Chekhanov-Elashberg algebra in the same way. It should give you the bordered Chekhanov-Elashberg algebra. So a non-trivial result is that the differential of this Chekhanov-Elashberg algebra equals 0. So this is done by embed your Legendrian tangle into some closed Legendrian knot or link, and then use the fact that your closed Legendrian knot or link gives you that this d squared equals 0. Yeah, but this construction is far from trivial, and so for the particular case here, you need somehow another version of Chicano-Falaciable algebra because you may have like base points appearing here. So that's why you have more generators in your bordered Chicano-Falaciable algebra. So this bordered Chicano-Falaciable algebra allows you to like reduce your computations to this local picture, and somehow CVAC also proved a push forward diagram for bordered Chicano-Falaciable algebra. Say if T is can be split into R and R, and by T we mean a Legendre tangle.
Sorry, before you go on, can you remind me, or give me an idea of how is this bordered, assuming just like a black box, how is it used in the proof of this isomorphism?
So I want to say that their proof somehow regards this thing as a global section of a sheaf. But in order to prove that this is a global section of a sheaf, you must prove that it's a sheaf of DG algebra. Somehow the first step is to prove that Chicano-Falaciable algebra is a sheaf of co-sheaf of DG algebras. But to prove this, you need some local to global like gluing result and co-restriction maps. So that's why this bordered Chicano-Falaciable algebra is really important. It somehow reduces the computation to local pieces, and somehow it enables you to compare this category to the most complex category, which is defined in a purely combinatorial way. So if you have local pictures, this category can be explicitly written down. And if you can identify like these two categories, then somehow you have like reduced all the things to combinatorics. So this is basically how you prove the theorem. And for this chief category, you can also reduce this to the most complex category. That's why I think the key point is the construction of Chicano-Falaciable algebra. So if you have a Legendre tangle, it's like split into left part and right part, and they intersect as the middle part V. Then you have a push-out diagram. So this tells you the fact that the Chicano-Falaciable algebra can be regarded as the global section of a co-sheaf. And in the meantime, it tells you that the augmentation category can be regarded as a global section of a sheaf of sets. But to prove that it's actually a global section of a sheaf of infinity categories, you need to do more work to relate this category to this category. Because this most complex category is defined in an explicit way, somehow it's easy to show that certain like isomorphism lifting property holds. So this is actually can be patched together to a sheaf, and the same situation is true for the augmentation category. And you do the same things here for your sheaf category, and finally you get an identification. So I think I'd better stop here.
Any questions for Ian?
I guess I'm really interested. I haven't. Sorry, I'll just ask my question. Can you give me a sense of why Aug plus is the global section of a sheaf, and like which sheaf?
So Aug plus is constructed from copies of Chicano-Falaciable algebra of copies of Legendre links, and so this basically comes from the fact that the Chicano-Falaciable algebra, you can define bordered Chicano-Falaciable algebra, and you can construct an augmentation category for Legendre tangle with induced Maslov potential. So somehow for every open sets in your real line, you have a definition of this augmentation Aug plus category, and somehow you show that they can be patched together. But this is not easy. So this is easy in a set level because it follows from the fact that the Chicano-Falaciable algebra is a co-sheaf. But to prove the certain isomorphism lifting property, you need to pass to the most category. So that's basically how you do that.
Minor question. So on the product on the left y, when you do the M2 with y plus with something else, you get a minus sign on it?
Yes, because it's not exactly the unit, it's somehow minus of the unit.
Yeah, that was sort of an unfortunate sign convention.
But that's not acting as identity.
So minus y plus is the identity. That's why the unfortunate sign convention.
Alright, more questions? Okay, yeah, before we start doing, there will be another discussion section after this, run by Vivek.
I think Vivek is going to calculate the sheep category for the trefoil. Is this correct? Somewhere?
Alright, yeah.
We thought we would do something nice and concrete since we haven't really seen much of the sheep side.
Alright, cool. So, what shall we do? Do we need a short break or we can just keep going?
Even I need a short break.
Okay, great. So let's say we'll get back in 10 minutes. So it's like a 6:05.
No.
505.
5 minutes.
505.
505.
5:05. Oh, sorry, my watch didn't. That's okay.